Good everyone, my name is Graphics. Today we want to solve a problem on crank effort diagram where we'll be looking at model 2. And the question goes like this. It says, the variation with time of the torque required on the driving shaft of a machine during one cycle of operation is given below, right? This is the table given. We are given the torque in Newton meter to be 10, 10, 120, 120, 25, 25. And the time in seconds is given to be 0, 8, 12, 16, 24, and 40, right? Now the question continues. It says, the shaft is directly coupled to an electric motor which exerts a constant torque and runs at a mean speed of 2100 rpm, which means revolution per minute. The rotating parts are equivalent to a flywheel of mass 20 kg with a radius of gyration of 500 mm. Determine A. The power of the motor neglecting friction. B. The percentage fluctuation of speed. Are we together? Now, the first thing you do when you come across questions like this, especially calculation enhanced problem, is for you to write out your parameters, right? Now, the parameter given here, we are given the speed in RPM, which is given to be 2100, the mass in kilogram, which is given to be 20. The radius of gyration can be either be written as r or k, but we're using k, equals to what? 500 millimeter. You convert it to meter, you divide by 1000, and that will give us 0.05 meter, right? And we are told to calculate for the power neglecting friction, and we should look for what? The percentage fluctuation of speed, alpha, right? In most cases, they make use of what? C sub x, but we make use of what? Alpha. Now, I will do one modification here. Since we are given our speed in RPM, I would like to calculate for the speed in rad per seconds, right? Now, recall, we know that our angular speed, right, omega, is given as 2 pi n over 60, right? Now, our n here is 2100. So when you do the needful, we'll say that 2 pi, pi is given as 2 over 7, multiplied by what? 2100 all over what? All over 60. And that is going to give us what? 220 rad per seconds. So that is the equivalent of our angular speed. Is that okay? So we proceed. So anytime we're talking about angular speed, we'll refer to our data here to be given as what? 2000, given as 220 rad per seconds. Now the first thing we'll now do, the next thing we'll do is to tabulate the reading that is given on that table on a graph, right? You can use any, just more like a sketch. So we are plotting the torque against time. So the vertical will be for the torque in Newton meter, and the horizontal will be for the time in seconds, right? Now we can use any scale of our choice, but let's just assume this is the 0, start from the lowest to the highest. So in terms of the torque, the origin here is given to be what? 0, right? Followed by 10, followed by 25, then followed by what? 120, right? You just put that way. We're just to sketch it out to know the direction we're about to take. Now, the next one we have the time starting from 0 followed by 8, then we have 12, we have 16, we have 24, and we have 40. You must not repeat any value. Is that okay? Now, we move. When the time is 0, right, the torque is 10 at this point here. Is that okay? When the time is 8, the torque is 10 also. So where time 8 meets with the 10 here, is at this point here, right? Similarly, when the time is 12, the torque is 120, right? So where they meet, we have what? This point here. Now, when the time is 16, the torque is still 120, constant, right? At this point here. Now, when the time is 24, the torque is 25. They are meeting at this point here, right? And when the time is 40, the torque still maintains 25, constant, right? So you see what I've done here? It means that when the time is 0, right, the torque increases to 10 Newton meter. And when the time increases to 8, the torque maintain the 10 Newton meter, right? It's constant. Then when the time increases to 12, what happens? The torque increases to what? 120. Are we good? Then between the interval of 12 and 16, the torque remains constant, 120, 120, right? And when the time moves between the interval of 16 to 24, the torque decelerates. And when the time increases to 40, what happens? The torque is constant. It maintains that movement, right? So this is what we just have here. So successfully doing that, we realize that this diagram here on this graph has formed some plane figure. And what are the plane figure? If you look at this, this is a square, right? A1, we call it A1, and this is a trapezium, right? We call it A2, and this is a rectangle, we call it A3. This is another trapezium, we call it A4. This is a rectangle, we call it A5, right? So we are going to look for the total area in this movement. So we'll call it A total, right? That will equals to A1 plus A2 plus A3 plus A4 plus A5, right? Now we know very well we're doing that by the side. A1 is a square, right? That is a rectangle. Since they are not the same, is a rectangle, to be length times breadth, right? And that will be the length here is the interval along the time axis. The difference in the interval between area 1, that will be 8, 0 to 8, right? That will be 8 minus 0, and that is still 8. Multiply by the height here, which is on the torque axis, and that is 10. So 8 times 10 is what? It's 80. So I'll put represent my A1 here to be what? 80. Plus, for the A2, it is a trapezium. So remember your velocity time graph, that is average distance traveled, right? That will give me, at this point here, 10 plus this point here, 120, then multiply by what? The difference in their time interval, 4. And that is going to give us what? That is going to give us 200 and what? 260. Is that taken? Another way you can do that is by dividing it into two. So we have the area of a triangle and that of a rectangle, right? And if I'm doing that, you get the same answer. So let's apply that and see. The area of a triangle is half base times height. So the base of this triangle here is equals to what? The difference between 8 and 12, which is 4, times the height, which is from here to here. Remember, you're starting from 10. So from 10 to 120 is 110, right? So when you say that 4 times 110 divided by 2, that's the half base times height. Then plus the rectangle here is given to be, the difference is 4 times the height, which is from here to here, and that is 10. So 10 times 4 here. So we're having 220 plus 40, and we still have what? 260. So any of the two you want to choose, you get the same answer. Calculating for A3, which is area 3, and the length is given to be the difference between 12 and 16, which is 4, and the height is given to be what? 120, right? So the area of the rectangle is giving us length times what? The height here, and that will give me 120 times 4, which is what? 480 Newton meter seconds. Similarly, calculating for the area 4, you see that area 4 is a trapezium. If I bring it out, I'll be having the length to be the difference between 24 and 16, which is 4, which is 8, and the height is given to be 120, then the other height is given to be what? 25. And the area of the trapezium is given to be what? Half A plus B times what? The height, where the A here is the height, which is 120, and the B here is the other height here, which is what? Which is 25. To multiply by what? The difference in the time, which is what? 24 minus 16, which is what? 8. So the area for the will now give us what? 500 and what? 80 Newton meter. Is that okay? Now similarly, we'll now calculate for the area 5 here. Realize that it is a rectangle here, and you bring out the rectangle. The height here for the rectangle here is given to be what? 25. The length here is given to be difference between 40 and 24, which is given to be what? 16. So the area of rectangle is what? Length times the height that we have here, which is what? 25 times what? 16. We'll be having what? 400 Newton meter. So we'll now see that my total area will now give me the sum of all the areas here, which is giving us what? 1800 Newton meter. Is that okay now? Now, the next thing we should do after we calculate for a total area is to calculate for what? The mean torque, right? The mean torque. So the mean torque is giving us what? The total area over what? The total time. Now, what is the total area here? The total area is given to be 1800 divided by the total time, which is what? 40. So 18 divided by 40, that will give us 45 Newton meter, and that is what? Our mean torque, alright? So from here, we'll be located on our graph. So we'll go back to our graph here, discover that the 45 Newton meter is on the torque axis, right? So, and it falls in between 120 and what? And 25. Is that okay now? So what I'll simply do here is to just take any points between 120 and 25. So take it as our 45, right? So let me assume that this stage here, this point here is my mean torque, 45, and this is where it is located. Is that okay now? So that will be the area of our shaded part. So we want to look for the area of our shaded part because we want to get what is called the fluctuation of energy, BE. And the fluctuation of energy, BE, which in some cases we'll call it delta E, right, is given to be the area of the shaded portion of this graph here, which is here, right? Now I want to consider just this graph here. Now we know very well that, let me name them. Let's say this is A, B, C, D, E, F, and what? G. Let me call it that way. Is that okay now? So if you discover that AB, right? If you discover that from AF here is not the same as what? The difference between 8 and 12, if you trace it down, right? As it goes up, let's call that 8 and 12. Let me say it to be P and Q. P and Q is not the same as AF, right? So it decreases as we move higher, it gets steeper. That is why AF is not the same as point B. That is why we will now say that the distance between AF is unknown, so we'll target to be what? S, right? But the distance between, let's call it to be what? RP, right? RP is the difference between 16 and 12, right? And it is the same as saying FE, right? Which is as saying BC. So we say that point is what? 4 and 4 here. How good now, because they are uniform from the bottom straight down to the top. Similarly, if you look at the difference between 16 and 24, right, is not the same as E and D. It decreases as it goes up, just like AF. So we'll call it Y is unknown. We'll have to calculate for it, right? So now, how are we going to calculate for that? Now I'm going to bring out this triangle out. Let me name the triangle. We'll say this point here, let's call it point M, and this point here, let's call it point N. All good now. So I'm going to bring this point out here, right? We'll bring point BMN out. So when I bring it out, we have it here. Remember that AF is somewhere around here. Start taking. So my MN is the difference between 12 and 8, which is 4. Right, I write my 4 there. Right, and my AF is X. Now the height of my my NB, the total height here, right, is giving us the difference between 120 and what? And 10, and that's 110. So from here to here is 110. Similarly, the difference between my BF here is going to be 75. How? 120 minus 45. So the difference between here to here is what? 75. And I'm going to do the same thing. What will I now do? I'll do the same thing for the other aspect too. Let me just put it close to it here. Let's call here to be Q, right? And here to be what? R. Is that taken? So if I bring CQR out this way, remember I'm having this part here, which is what? ED. Now we'll do the same thing we did in the previous one. The distance between Q and C is the difference between 120 and 25. So 120 minus 25 will give us 95. So the total height of this here is what? Is 95. Similarly, difference between C and E is difference between 45 and 20, which is what? 75. Right? So look at the two different triangles that we have here. So I will calculate for X for the first triangle, and I'll calculate for Y for the second triangle using ratios of what? Of sides here. Is that taken? So if you look at this, they are similar triangles. So I'm going to say that since I'm looking for X, I'll say X over 4 as along X is equals to what? 75 over 110. See what I did about it? The base of the smaller triangle over the base of the bigger triangle is equals to the height of the smaller triangle over the height of the bigger triangle. So if you have that, you make x instead of the formula. My x will now be equals to 4 times 75, right? Because the 4 is going up to multiply 75 all over 110. And if you multiply 4 times 75, you'll be having 300. And 300 divided by 110 will give us 2.72 meter. Are we together? Similarly, on the other triangle, we'll do the same thing, saying the base of the smaller triangle, which is y, divided by the base of the bigger triangle, which is 8, is equals to the height of the smaller triangle, which is 75, divided by the height of the bigger triangle, which is what? 95. So if you make y the solid of the formula, my y will be equals to what? 6 equals to what? 8 times what? 75. And that is 600 divided by 95, and that will give us 6.32 meter. That's our y. So we have successfully gotten the value I'll input it here now for x and what? And y, right? Which is 2.72 and 6.32 respectively. So in doing that, so what we should now do here now is to what? Calculate for the area of that shaded part, which is the BE and beta E or delta E, that is fluctuation of energy, will now be half A plus B times height. So A here is the addition of the total value at the base of the trapezium, which is 2.72 plus 4 plus 6.32, right? And that will give us what? 13.04. Plus B is just the total distance at the top here, and that will give us what? 4, right? So 4 plus 13.04 is 17.04 multiplied by the height, which is 75. Altogether, so by the time you do the needful, 17.04 times 75 is 1278 divided by 2. So we say that the area of shaded part is equals to the BE, right? That is fluctuation of energy, which will now give us 639 Newton meter. That is what we have there. So from here, we've gotten our fluctuation of energy. So we'll now look for the first thing we're told to look for, which is our power of the motor. So we know power is equals to the angular speed multiplied by the mean torque. And I will know angular speed, as we've written our parameters earlier, is given as what? 220 multiplied by what? 45, and that will give us what? 9,900 watts, which is 9.9 kilowatts, right? After that, we will calculate for the percentage fluctuation. Is that taken? Or speed, given as alpha, while in most cases they call it C sub x. So our fluctuation of energy, beta E, which can be written as delta E, is given as the moment of inertia multiplied by the fluctuation of speed multiplied by what? The angular speed square. So, but we know that since our moment of inertia is not given, there's a relationship that says I is equals to mass times radius of gyration square. So if I input it there, we'll have my beta E, which is function of energy, is equals to, in place of I, we have mk square, then times alpha times omega square. So if you make alpha sort of formula, alpha will be equals to what? Beta E over mk square omega square. So my alpha will now be equals to position of energy is given as 639 all over my mass is given to be 20 multiplied by my rate of gyration, which will be 0.5. If you convert it, we are giving it as K. So to give us from 500 millimeter to give us 0.5, right? So we have square there, multiplied by the omega, the angular speed is given as 220. So we have square there, multiplied by what? We have square there. So that's what we have there, right? So what we have here now, we'll now say that my alpha here will now be given as 639 all over 5 times 220 square. Is that taken? So my alpha will now give me 639 all over 24,200, right? So my alpha will now give me 0.002638, which is given in percentage as 0.2638%. So that's what we have. So if you have found this video helpful, please don't forget to like, subscribe, and also share the video. Thanks for watching.